Hello, my name is Munadir Ahmed and I'm an applications engineer at PLECS. This is a follow-up to the Introduction to Thermal Modeling in PLECS tutorial video where we provided loss information to a semiconductor switch and defined a thermal model for the system. The circuit we have built includes a heatsink and a thermal resistance to the ambient temperature. However, the thermal library provides the building blocks to create more complicated thermal systems, including the modeling of complex cooling schemes. Controlled temperature and heat flow components can be included for custom designs. Our first step is to use a more detailed thermal description for the IGBT than the one that was shown in the first video. If we now open the IGBT parameter window and choose the detailed IGBT option, we can then view the loss tables by clicking Edit from the drop-down menu. You will immediately notice that multiple surfaces for the losses are defined for several temperatures. This really highlights the top-down design approach that PLECS facilitates. Users can quickly and easily obtain ballpark estimates on device losses and temperatures. As a design matures, users can add more detail to a model to get more accurate estimates. The thermal equivalent circuit of a component describes its physical structure in terms of the thermal layers from the junction to the case. Each transition consists of a thermal resistor and a thermal capacitor. They can be edited in the Thermal Impedance tab of the Thermal Editor. The thermal equivalent circuit is specified either in Cauer or Foster form. In this case, we have specified a thermal impedance for the device junction to case transition as a first-order Cauer network. More details on the thermal impedance can be found from the documentation or by pressing the Help button. Rerunning the simulation, we now obtain more representative loss information. This is because we have made the loss calculations to be temperature dependent by adding further temperature profiles in the tables. Notice that the temperature of the heatsink is climbing during the transient simulation, and after simulating 5 milliseconds is around 27 degrees. The requirement of power electronic systems are often specified at steady-state conditions. One way to obtain the steady-state operating point of a system is to simulate over a sufficiently long time span until all transients have faded. Typically, the thermal dynamics of a power electronic circuit are much slower than the electrical behavior. To analyze the steady-state operating temperature in simulation via this inefficient method can be very time-consuming. Built into PLECS is a steady-state analysis tool which will allow us to quickly calculate the temperature of the heatsink, in this case, without having to change the simulation time to an unnecessary large value. In PLECS standalone, the analysis tools are accessed from the simulation menu. More detailed information on the analysis tools is provided in a separate tutorial video, but for now we will show a simple demonstration. To create a new analysis, click the button with the plus symbol. We are choosing a steady-state analysis and will need to specify the system period. In this case, this corresponds to the period of the pulse generator, which is 1 millisecond. If we enter this in and click Apply, we can then start the analysis and find that the steady-state temperature is closer to 29.6 degrees. The steady-state analysis is a very useful tool for getting a quick estimation of the operating temperatures that a device will experience and can therefore be used as part of an iterative design process. In addition to knowing the steady-state temperature cycling of the device junction and using this information to size the heatsink, we may also want to know the steady-state losses of the IGBT to calculate the converter efficiency. This can be done in PLECS using the probe block and a couple of filtering blocks from the control component library. In many cases, a factor of interest is the average power dissipation of a semiconductor device. The average conduction losses of a component can be calculated by averaging the instantaneous conduction losses, probed in watts, over one switching cycle. This can be done using the periodic average block. In PLECS, the switching losses of the semiconductor devices are provided as energy packets measured in joules. These energy pulses need to be averaged using the periodic impulse average block over one switching period to find the average switching losses. We have actually already selected the conduction and switching losses of the IGBT in the probe at the bottom. We then specify an averaging time for the filter blocks. 1 millisecond corresponds to the switching period of the IGBT as defined by the frequency of the pulse generator. We will now look at the scope with the losses. The total losses of 4.5 watts after the first switching cycle is the sum of the average conduction losses and average switching losses. The details for these calculations can be found in the component description of the two filter blocks. This concludes our introduction to thermal modeling in PLECS. For more information on thermal modeling and the PLECS probe, please consult the PLECS documentation of the demo model library, which shows several examples of pre-built thermal loss descriptions and circuits. Thanks for watching.